Hello, my English speaking friends. This is my first video in English. Well, just kidding. I can speak a little bit closer to normal. Let's try and understand the concept of wavefront summation, made up by me almost entirely. Well, the first time I saw this thing before I started to think about it and trying to extrapolate it onto bigger, higher dimensions was in a video where it was used to explain the summation of squares. 1 squared plus 2 squared and so on up to the number n squared. Yep. As you might know or not, this adds up to this, too many theses. This adds up to a formula, to a fraction, which I yet another time cannot quite remember. I think it's something like n times n plus 1 times 2n plus 1. I think so. Yep. This can be proven by induction, but the proof by induction isn't the derivation of a formula. Well, yeah, if I try to add here, if I try to take some number k and add the next step to the formula for k, so I'm trying to add k plus 1 squared, I could just revoke it by rework them. I can speak, but not really properly because I sometimes just forget how to talk, how to say some of the words. Yep. I could rework it by algebra and just show that it equals to the next phase, like k plus 1 times k plus 2 and 2k plus 3 divided by 6, as it was going to be from the very beginning. And yeah, this can be proven by induction, but I'm not gonna do it. I'm gonna show you how to derive this formula using what I like to call wavefront summation. Let's first reimagine our series, our sum of the squares. Wait, no. Let's reimagine it as something a little bit other. Let's recall what is a square. A square is a number multiplied by itself. 1 times 1, 2 times 2, 3 times 3, and so on to the very end. Yep. But what is multiplication? Multiplication is basically an iterated summation. So we have 1 multiplied by 1, 2 multiplied by 2, so it's two of those addends. Two addends each equals to the number 2. And then 3 times 3 means we have to add 3 of that number, 3 copies, and then 4 times 4, of course. And what we want, and I'm going back to the stereotypical accent. What we are getting here. And next, n times n. What is this thing actually? This is a triangle, I think. This is clearly enough a triangle with a 1 at the top, then 2 of the 2's, and 3 of the 3's, and 4 of the 4's, and maybe 5 of the 5's. Let's see, let's try. And what is the action we are gonna perform here? The action we are gonna perform here is to double this triangle additionally to the one we have already. So we get 3 of them, 3 copies, and then we are gonna stack them upon each other. So one triangle goes like so. It starts with the 1 at the top, and it ends with a row of ends at the bottom. So it's kinda raising its numbers, going from top to bottom, left and right. And if we looked at it from a different angle, from a different point, we could say it makes the numbers, the entries, less and less, going bottom to top, or going sideways. It does not affect the numbers. What are we gonna do now? We are gonna add here some more triangles, exactly 2 of them, but with other configuration, exactly like so. One of them will start at the bottom left with a 1. Here is a minus, and there is a minus, there is a 0, and this is also a 0. And the last one starts here. This is a 1, plus and plus, minus and minus, and 0, also 0. And what we get here? We get here this fabulous thing. We could even say this is some vector thing, because one of the triangles exhibit this kind of what could I call it? This kind of behavior. It adds on those ways, and it takes on those ways. And when we stack another triangle, we make it add on those 2 ways, and take is blue on those 2. And when we also, well, I think I could try to add those black arrows too. And the last one, we stack on top, it adds on those directions and takes on those two, and also it is neutral on these. I don't know how to use the words this and that in English. Would you mind tolerating this? Let's see next what we get here. We can clearly, almost clearly see that we have a 0, a minus, and a plus, a minus, and I guess a 0 should also be here from some kind of operation. I mean, we really do get plus and minus on every direction. So every direction is neutralized now, and we just have a new triangle that has all of its edges equal. So we just have to work out what are those edges, and they exactly are the sum of the points of our triangle. If our triangle is n on a whole side and 1 on a vertex, we just add them up and get to n plus 1. So we get a triangle, and every one of its entries is n times 2 plus 1. In other words, on our example here, we get a triangle composed of 11s. If I take this triangle and reverse it according to the method, we can clearly stop seeing anything, but I am still gonna try to do something. Yep, we can see 1 plus 5 plus 5, it makes an 11 on the top. We have also 2 plus 5 plus 4, which also makes 11, and here we can see 4 plus 3 plus 4, or maybe 3 plus 4 plus 4, which also makes an 11, and like so we get a triangle composed of 11s. And now we just have to work out how to sum a triangle of equal edges. And here comes our old friend Gauss, who, as we know from a legend, from a I don't know how to say it in English, but there is a story of him being a school kid and a teacher giving him, or giving to the class, the task to add up all the numbers from 1 to 100. And what does Gauss do? He does absolutely the same thing we are doing now. He makes a wavefront that neutralizes this growth of the numbers. He just starts it over from the top to the bottom, making every entry 101. Oh no, this is plus 1 and this is 101. So then he just adds them up. How? Like so, by multiplying, because he isn't as willing to calculate every addition. He knows that multiplication is much simpler and faster. But then he has to divide by 2 because he just recently added them 2 times. Every number 2 times. This and that. Every number has its copy. So, yeah, this is actually how to know how many entries there is in a triangle. Because if we get a triangle of, let's say, 3 rows, we can just flip it and add it here to see how it all becomes 4 and 4 and 4. So the 3 from the number of columns or rows, better I say rows, the 3 from the numbers of the number of the rows, from the quantity of the rows, is here, and 3 plus 1 from this neutralized equal spacing is here, and we have to divide by 2. So this is a triangle, and that thing is what we have in this triangle in every entry. So to calculate the final sum, we just multiply this 2n plus 1 by the triangle n times n plus 1 half, and also divide by 3 because this originally is a sum of 3 copies of the same triangle. And like so, just like so, we get our division by 6. We get our n times n plus 1 times 2n plus 1. Exactly like so, we end up with this formula without using any induction. And also this works in higher dimensions. It works for simplices or elementary pyramids, as one can possibly explain what a simplex is. In 3D for the tetrahedral numbers, no, what do I mean tetrahedral? No, tetrahedral number arrangements, and in more dimensions as well. Also, this works for triangles with reversed fronts, with reversed wave fronts. If we start with number 5 and then go down, lowering the number 5 to 4s, 3 3s, 4 2s, and 5 1s, we still can add them up using this formula, because all that we need to do is to add the 3 corners, making a 7, then multiply it by the triangle, 5 times 6 by half, yeah, really, times half or by 2, well, don't mind it please, and divided by 3, yeah. And like so we get this sum. This sum is now 35, and I can't remember why it is important, this 35. Is it maybe some triangle number or a yeah, this really is the simplex number, I think. I don't remember why 35 is important. 211. What is 211? This is yeah, of course, of course, of course. This is a simplex. If we get two of them like so and two like so, we draw the simple simplex of four spheres. Yeah, exactly. This is what we use, what we can use to make the simplex numbers, basically. Yep. So this is it. I hope you didn't hate the audio quality as much as you did hate my pronunciation.